But then still, let me try, see if I can do that, right? Still have, and then you guys can leave if you want, right? Let me still try, but let me pause the record. Okay, so let's start the demo, but not just demo, we want to take this opportunity to understand the layout and the structure of FinFET. I think this is more important than anything you have learned so far, although it might not appear in the exam, but this is really something very useful that I'm going to talk about, right? This is from this paper. You can take a look from Qualcomm. At that time, they're still exploring whether they should use FinFET for their device, maybe 10 years ago, right? So, but now they are doing nanowire already. So you have this substrate, and if you remember, we have fin. These are the fin. You have multiple fin in order to increase the current, right? You cannot control the width and the height, right? Due to patterning limitation. Then you have this gate wrapping around. Here you cannot see it clearly. These are the oxide isolation. So this is about FinFET. And on the same structure, we also have P-type. And because it's about FinFET, they need to bias the P-well, right? So they have a P-well type. But in the Cadence one, we don't need to do that. They don't have that. I think it assumes SOI. Okay, and same for here, you have the N-well, right? Regarding contact, this is a little bit difficult to understand for you, but if you do a cross section here, cut it. You have this fin, right? And this is the gate, right? On top of the fin is the gate. Bottom is the fin. And the gate wrap it around. And actually, no, in this direction may be opposite, sorry. In this direction, maybe you can think it as the fin is here. Okay, so this is source, this is drain. Think it this way. Okay, so this is source, and then gate is wrapping around inside and outside of the screen. You need to have a contact to it, right? So you have isolation to enable self-align source drain, so you won't short them together. Difficult to see. You need to spend some time to look at it carefully, and if you have a question, you can ask me. And here is also difficult to see, but this is source. This is drain. Remember the diamond structure I discussed earlier? So this is the fin underneath it. In the middle, then you have the gate wrapping around. How does the gate look like? You wrap around with the high K dielectric hafnium dioxide, and then metal gate to adjust the work function, and then you have metal fill, and that is the gate. Difficult to understand now, but any questions? No, this is the gate oxide. So imagine I have the fin here, right? This is removing everything. This is the fin. Do you just see this yellow one? This is the fin moving from left to right. So in this part, I need to wrap it around with the gate, right? So the first thing I will wrap around is the high K dielectric. Now, because of the process, if you cut in this way, you will see this oxide. Just think about when I deposit oxide, you will deposit everywhere, not just on top of this yellow one, but also on this side wall. Yeah, and then I deposit metal, again, not just on top of the yellow one, also side wall. That's why you see this when you cut it. Okay, just like the cake, tiramisu or something. Yeah.
The previous slide, you had the substrate.
Yeah.
So that P-well is short substrate, right? So if you bias the P-well time, you bias the substrate.
You do, right? This bulk, this just like a triple, not triple well, just a regular bulk CMOS, right? Your P well, you are tight, you bias all the P well and P substrate. But then here N well, you bias by the N well type, right? So you probably will bias this at 1 volt, this bias at 0 volt, right? Now I go to 1 volt instead of 5 volt because FinFET are using something lower than that, or even 0.8 for 14 nanometer. Okay. It has layout effect. So let me skip that because I want to go to the layout. Now, if you use Cadence, it has some document. Yeah. Multicoloring. I don't know about that. What's that? Okay. Thanks for saving my face. Then, okay. So here is the FinFET structure in Cadence. I want to show you this. You have the active, which means the source string. It connects to something called local interconnect active. These are some CLSI that you can do the local routing. And then you have a weir connect to M1. For poly, you have the local poly interconnect. I think LI stands for that. Maybe I'm wrong, okay? Just for this Cadence 14 nanometer. And then have the weir connect to the metal 1. That's how you connect it, okay? So before I do this, the best is just go ahead to do the layouts or whatever, right? So again, I will open a terminal. I go to TCS. Then I just do what we have been doing, S45, that will involve the virtuoso. Now, because of time, I will not do the schematic layout, but I will try to do the, I will not do the schematic, but I will try to do the layout. Again, you can leave anytime. I just open the schematic I already done at home. You see, everything is the same as 45 nanometer, right? How do I get this? I go to this one, and then I go to CDS FF MPF, the library, and then I choose, for example, standard VT. Not here. Standard VT. Star, standard VT. Right? So I choose, for example, P1S, then I move to here, right? So everything is the same except I'm using a different library. That is the first thing. And of course, when you create your library, you need to attach to this library, right? Just like what you did for 45 nanometer. Now, if I click on this, left click, right? And then right click, look at the property, or you can press Q. You'll find something interesting. It has something called number of fins per finger. It also has something called number of fingers. So what does it mean? I do have a slide to show you. This is the layout. Here is source, here is drain, and this is the gate, and this is the fin. Is that okay? Now, if I say one finger, it means here I only have one fin. I'm sorry, wrong. Here I only have one finger. This is finger. Yes, it means how many gates you have. It means increase the width, effective width. And then I only have one fin, means from here I only have one fin. Now, remember, this is not really a fin, I will show you later. If I say I have two fingers, then I have this. So why then, how does it work? You will find that this is gate, this is gate, this is source, and this is drain. So you are actually have two transistors in parallel. The currents will go in this way. Right? Imagine, so you have a circuit, the source will come here, and then they go to here, so you have two channels. It means you double the width of your transistor. Okay? Yeah. Yeah, that is the, so since you talk about this, let me also discuss this very soon, right? So if I say two fingers, again, I have two fingers, but two fin, you see this is wider, but you do not see two fin. Why is that? Let me talk about this first. If you look at the layout, a real fin is very thin. It's only 14 nanometer. Between the fin you have a distance. Their pitch is 48 minus 14 nanometers. So here I have 3 fins, 3 of them. Now in your layout, you don't need to lay out them one by one. You just put the whole block, and Cadence or the PDK will automatically convert for you into 3 fins. Because this, you cannot change them. So that's why they know how to convert it, right? So for example, if you look at this is 48, and then the width is 14, so from here to here, I expect to get about 62 if I have 2 fins. I already done the measurement for you. Do you see that from here to here is 62 nanometer from here to here? Can you see this number? Maybe you cannot. This is 0.026. Again, it is from here to here. From here to here is 48 plus 14 equal to 62 nanometer. So when you say 2 fin, it just draw a box that is 62 nanometer for you. But when you manufacture, you will break this into 2 fins.
Also negative mass.
No, you don't think about negative mass. They're going to convert it. So eventually you print this. In reality, you have something called manual, all these things. Because this is a so thin, you need to have a certain pattern. Otherwise, they cannot print it. You want to provide periodic pattern. But this is irrelevant, actually. But here, they mandate you to have this type of spacing. And that's why you don't need to draw them. You only tell them how many fins, then you just draw it for you directly, right? So here, we are not drawing 2 fins. So in reality, we expect that we will have maybe 1 fin here, and then 1 fin here. Okay? And this total is 62 nanometer. Yeah.
So those fins end up actually when they get fabricated on the
Yeah.
end of that rectangle?
Yeah, for in this case, correct. They will fabricate it in this way. Okay? So you need to trust that that is how it works.
They've done this way. I don't know the fit itself.
I mean, because it is already fixed, they just make it simple for you, right? You just draw the, yeah. Now, this is the poly gate. He just said something. Why we have this poly gate here? This is super narrow, right? If we look at the layout, it doesn't say how much, but maybe in the order of 20 nanometer or smaller. There are 2 reasons for this. One is for patterning. You want to have periodic structure so you can print them well. It's easy to print small features which are periodic, okay? And other is the so-called layout effect. Remember that we try to enhance the performance of FinFET by using stress? Remember that? Now, if you use stress, it depends on your environment. If you think about this, if I have this fin, and do you remember that we say I try to add some stress silicon germanium here to get some compressive stress to this guy? Right? Push the gate. These are the gates. You remember this? But similarly, you are going to also do this outside, right? Now you see the boundary. This is very wide. So you get a lot of stress. This and this won't be the same. If you only have 2 fins, then you will not get the right stress. That's why you need some dummy silicon, dummy poly, dummy gates outside. So the main transistor will get the stress you want. Otherwise, you get a lot of variation. Yeah.
So I guess the first one there from the left side, because we use this is going to get fabricated.
No, this will be the dummy.
The stress being.
No, stress won't really change the size too much, just in the order of 1%, right? But we're talking about enhancement of mobility. But in terms of printing, I don't know either wider or narrower. But it is dummy, we don't care. Yeah, and that's why we have this layout effect. So when you do the layout, cannot think that, oh, why you don't simplify it, right? Because you need to consider the manufacturer subsequence, okay? So you're already 8:45. Please feel free to leave, but I will continue until no one here. So, so now, then what will we do, right? I'm going to just maximize the screen. And then now, just like what we usually do, like type F, then you maximize. Then I go to launch. I'm going to use layout GXL because it has a feature that is very useful. Now, I won't open existing one because existing one was, yeah, anyway, I just create a new one, like what we do for the 45 nanometer. And I also need to just use my mouse. I'm recorded, yeah. I know it's late. Feel free to. Let's see if I can make my mouse work. Yeah. So now you have this, right? So I already created the, I am going to change the size because you usually make it into 2 parts. I type F, lowercase f, I can see the full size. So let's take a look. I'm going to say connectivity, like what you did, generate all from sources, right? Like what you guys reminded me, I need to create label S in order to match the pin. And here I use M1 as the pin, right? And then you can apply to all of them. But now it is there by default. So make sure to use M1. Then I have this. Now I have all this label, which is very annoying. I should have changed it earlier. I highlight it, and then I say property, right? How do I change the height? So I can change it. So again, I move my cursor to here, click on it, left click, and then right click, and then properties. And then the height, I'm going to change to 0.1, and then apply. Okay, and then I click on another one. I should have done that when I create it, but that's okay. Click on another one, then now it becomes out. Just want to share some of the skill that I learned. Actually, I'm not good in doing the layout. I don't have the experience as some of you have. And that's okay. And then click on this, type F, zoom out, and then Shift F to see the layout. Now you see the layout, right? So let me just maximize it. Again, Shift, just F, lowercase f. I use the middle button to scroll it. I have a mouse. Then I can zoom in, zoom out. Use the right button to, not right button actually. I need the arrow key. How to pan it using mouse? I don't know. Just use arrow key, right? Arrow up, arrow down. Do you see this? Now, if I just try to measure it, type K, right? So let's measure this one, top to bottom. This is 62 nanometer. So let me turn off the light. Right, so you still cannot see it well, right? But trust me, this is 62 nanometer, right? I go to the left. I say only click on the use one, then that will be easier, and then turn on everything. And let me explain one by one. First, end well. This is for PMOS, end well, right? And then active. Active is basically where you define the fin, right? Remember this one that I say that this region, fin, right, and spacing. Yeah, including the spacing. Altogether, spacing is about 48 minus 14, right? 32, okay? Right. And now I turn on the cut active. So they have some special treatment to cut the active, which I don't know exactly what it does, but the poly cuts and active cuts are important in the layout to avoid shorting and also, because the fabrication is very complicated. And you see that they also have a fin area. I guess that is because you tell this is the fin and then you try to do something, maybe related to stress or whatever. So this I don't know why. And then we have PSVT, here, this one. Do you see my mouse? Look at the, oh, that is very bad, yeah. Yeah, the bottom is bad, yeah. NSVT is to say what is this? PSVT, the PMOS implant. So not just implant, including later growing silicon germanium instead of silicon carbide, right? And then NSVT, now you know this is N-type. And then poly, it's not real poly, it's actually a metal gate, right? But you may have replacement gate, which we did not discuss. They may start with poly. But this is the gate, but we continue to call poly. Only one, right? One gate, one finger. But you have all this dummy next to it for the stress purpose and also printing purpose. You have a poly edge, right? So all these things have different layer, you can do it. And then you have this local connect active, which refer to the the connection to the silicon germanium or silicon carbide at the bottom. Then metal one and test. Okay? Yeah.
What are those neighboring blocks that?
Yeah. But it is related. I think they just call it different name. It's a part of the dummy poly. But they also have the role with this active cut, I believe. So at the active end, you have the fin, the ending of the fin, right? I think they need to do some correct processing in that region. Yeah, which I don't know exactly what it is. This is just a generic one. When you get a PDK from a foundry, probably it's different, right? But we just learned some basic thing for now, okay? So now my goal is to do the routing, and again, anytime, feel free to leave. So I have this, right? So maybe I just want to show you something. If I right-click, and then change the property of this, no, it doesn't work, right? I need to click on this one first, and then right-click, and then property, then I can look at the cell of the PMOS, and look at the parameter. For example, what if I do 2 fingers? Then I apply. Then do you see that it becomes 2 fingers, right? And then I can also have different number of fins. Let's say 4 fin. Apply. Then it's much longer, right? Then I have different fin. But of course, I don't want to do that. Just undo. You can put U, press under, lowercase u, right? Then you can do that and save it. Okay, so let me start the connection. So how can I do the connection? First, I want to connect the gate together. Now, I already know the design rule, right? Because I ran into problem when I tested earlier this weekend. So I am, but maybe I forgot something. But anyway, what I'm going to do is to zoom in, Shift Z, or use the scroll button. First, I want to extend this poly out, right? So I'm click on this poly, and then I will just create a shape. Or maybe I can use wire. Let me start with wire, and then I just put here. I'm going to extend it to here, right? So oh, that's too much. But I don't want to change it. I just type escape, and then I Shift Z, and then use arrow to go down. So again, I Control Z to zoom in. And somehow, why this is already extended? Okay. Yeah. Not yet. I'm doing, no, because the metal does not go there direct. That's what I'm showing you. Just hold on, right? For example, I start with poly, right? So now I'm also still routing poly, create wire, right? I'm going to route this one, click on it, click one, and then move your cursor up, and then just double click maybe, right? And then I get extended poly, okay? So how do I connect it? I don't know, I don't use metal directly. I'm going to use the, uncheck this one, Li poly, this one, okay? So I'm going to do connectivity, create wire here, and then I will try to connect from here, but it doesn't let me do that. So I need to create a rectangle instead. So I do escape, Control Z, zoom in, right? Zoom in, and then I'm going to maybe zoom out a little bit, create shape, rectangle, so that I'm creating Li poly, right? So I'm going to click from here, and then connect this to here. This won't be enough. Later, the DRC is going to complain, but I just do this now. Yeah. So is it a different layer? You can say it is different layer, but let's look at the document from Cadence. Do you see that? Just due to the fabrication process, you can run poly, but in order to go to metal one, you must go to Li poly and then via and Li1, just because of the process. And I believe this is like the silicide or something. And why is so complicated? Because look at this guy. Your is not really the gate. You actually have a trench. Depends on fabrication process. In this case, it's a trench. This one will be the LiPo. Okay, so your LiPo can be everywhere, but your poly might not be able to do that, right? Or depends on the technology. Okay, but anyway, let's only learn from the rule. The rule is you need to go to Li poly and then go up. No, you still need via. This is just the definition in this PDK. You don't need via to go from poly to Li poly.
So this is a particular.
Yeah, because what it is drawing to you is what you will get connected. The physics is not really, you don't need a via, maybe itself is a via. Why don't you think it itself is a via, a big via, how about that? But your via can be very long instead of just holes.
So here the V0,
Yes, V0, V1 are vias. So I may say something wrong, but so I guess that this need to be overlap also, right? So I type escape and I want to extend it, so I'm going to type stretch S key, and I will try to, no. Okay, on this again, S. Yeah. No, but
Press hit, use the move and press X, and now it will force. There.
okay, thank you. Yeah, so as what they said, right, you press S and then partial select. Sometimes it works, sometimes it doesn't. So same for this one, right? You go up and then you click on it and then you extend more so that there is overlay, right? So I forgot about the DRC. I also believe this one need to go out, but let's do that later. Now, then you want to connect the metal one to here, right? You can just create a via. Create via. Now this time you want to connect it to poly contact, right? So you will, is that poly contact? I think so. No, actually metal one to LiPo. Okay, metal one to LiPo. Right, so I'm going to click on here and just drop it. Okay, escape. Now with this, then I can just finish the routing of this guy. Right, wire. Right, of course, this one got shifted, but let me just click on here. Right, then I zoom in, this is ugly, so I'm going to click on this and then say M, move it up, so it will look a little bit better. Oh move and Control Z to zoom in so I have a better control. What?
Your snap setting.
Okay. Okay, so I save it. Now, it's supposed to have connected, so how can I check it? That's one thing, maybe some of the big, that's why I start with GXL. You go to connectivity, net trace, and then add. And then you just hold your mouse button here. Then you see that it got connected to the gate. Okay, so this is a pretty useful feature. And now I score my mouse key, right? So I know that this is connected, although it might still violate the DRC rule. Because when you say connectivity, net trace, add a new net trace and just put a cursor over it. You highlight everything that is connected, yeah. Okay, and then what do I need to do? I need to get the drain output, right? So for the same thing, I'm going to extend this one downward, but I cannot put metal, right? So this might be a lousy connection, right? So we need to think very carefully, but for now, let's just do something very lousy. I did not think about this, so let me just open the LiAct here, okay? So I'm going to just, no, actually I need to, yeah, this is LiAct already, right? So create wire from here. I just connect them together, right? Maybe this is not a good way because this might have a bad, no, I mean, this is a good way for, this is local interconnect, right? But maybe it has a larger resistivity or whatever, or capacitance has a problem. But the reason I do that is because I cannot put metal one here, or maybe I can put it here, but still I need to go through, right? So let me just leave with this. So now again, I need to drop the connection, the weir. But in order to do that, I actually want to first create a wire for metal. Right. I click on M1, and then I connectivity, create wire. Maybe I start from here. So I know the location, approximately the location. Okay. And my goal is to drop a weir, right? Maybe I should drop it first before I connect it. So I'm going to create a weir. But this time is to where? Is to LiAct, right? So I'm going to put it here. Right? So I need to connect this LiAct from left to right. So I zoom in and then I highlight this. Maybe I just go ahead to create a box. There might be better method. Create, shape, rectangle. And then how about I try to create from here to here, right? I don't know if I violate any DRC rule, but I connected them together, right? So if you want to check the connectivity, net tracer, add, look at this. Connectivity, net tracer, add. There's some problem with this Y. Connectivity, net tracer, add. And you see it is connected to the drain, right? So I know I did that successfully. So now I need to connect this guy to the top also, right? The top is the VDD. So I will And I think this is ugly, but anyway, let me just route it. Again, I will just do a ugly thing. You completely using the Li interconnect, Li active to do the connection. Okay, I will bring this to here. And I'm going to drop a via. I say create via. Now, because this is PMOS, I want to connect it to the N-well tab, okay? So, Control Z, I should click here so I can do Control Z, I can do arrow, Control Z, arrow to move, right? And maybe I will just put it here. I exceed the boundary, but I don't care now. This is just a demo.
Does the cell allow you to create a
Well tap, this is well tap, right? This one already helped me to create the well tap. Right, anyway, so I created this. I think there will be DLC problem. But again, if I check the connectivity, net tracer add, it does connect VDD to the top, to the source of PMOS, right? So I will do the same thing for the NMOS. I create wiring, yeah. We need it to overlap. There will be DLC error later. So, yes, correct. We will talk about NWell later, right? So I just extend this. And then again, I zoom in, I go down. And then what do I add this time? I'm going to say create via. Now we will do the P substrate. Man, did I did the wrong thing just now? That should be N-well, right? I want substrate at the bottom, right?
Yeah.
Because this is N-well.
No, this one is P sub.
Yeah, this is P sub, sorry. Okay, I have the P sub here. So maybe on the top, I make a mistake. I thought I did N-well, but so I click on it and then press the delete key, right? So I need to do it again, create, via, yes, thank you. And then we will do N-well, okay? Yeah, N-well is the right one because you will see the N-well. And then again, I highlight this window. I cannot. So that I can zoom in, Control Z, and use the arrow to help me to navigate. And then I put it just that it overlap.
This part.
Yeah. So I'm going to click on this, and then as I move, click on it again. So I move it to the right place. Yeah, if I don't do it right now, maybe I will run into DLC issue later.
C is.
Correct, but for example, this type of corner, it may complain. So now I want to okay. Save. So we are done actually, right, with the layout. So let's do a DLC. So I'm going to the